right, let's go ahead and get started. The rest of the crowd will, I'm sure, arrive. My name's Norman Lastovica. We have a special guest star today as a co-presenter, and this goes back 15 years, 20 years. Yeah, we the origins of this idea for a presentation came back from a long time ago, and we've sort of had fun with it as a boxing match and a comedy show and a tragic Shakespearean drama. Anyhow, what I'd like to do today is share with you a little bit about our methodology for performance analysis and improvement on computer systems with a focus on VMS. My background is not terribly important. However, before I started, like my first job in industry, I was writing bit slice microcode at the time with a 10 microsecond cycle time, I think. And I was very impatient with writing microcode that executes 1 million times a second. We use logic analyzers to play with it. I am just as impatient and frustrated waiting for the DCL prompt to come back on my brand new x86 system when I compile a C program. So I like computers to go fast. I do not like to wait. And I think that drives a lot of my professional work. So what I will tell you is when I get called for a performance problem, visit some customer site somewhere, the big picture is interact, interview, gather information, try to put a picture together of what we're looking at. I don't know your application. I don't want to know your application, but I want you to tell me what you don't like about it. Oh, it's slow doing this. It's having a problem there. Okay. And so then we start to develop a picture and we start to follow the evidence. And I'll share with you some stories about how what the customer tells me sometimes is evidence and sometimes it's not. And they'll have decided how things, they'll have decided what the problem is, even though it has nothing to do with the problem. And we'll share some stories that hopefully illustrate some of these behaviors. So at the beginning, you just ask a bunch of very simple questions. Inevitably, somebody will say, oh, it's slow. Okay, what is it exactly? Tell me, is it the screen transaction? Is it the time to process the batch? Whatever it is, define it. And I'll have a whiteboard or a piece of paper and I will write down what they say so that all of the people in the room are talking about the same thing. Did it ever work? So sometimes everything was fine yesterday and it's bad today. Sometimes it was fine in January and it's bad today. Sometimes it's never worked at all. So I want to find out am I debugging a big brand new problem that we introduced yesterday? Am I debugging something that's never worked? Or am I trying to understand why it gets worse and worse and worse over time? Very important because the strategies are much different. What changed? And what's the answer? Nothing. Nothing. I mean, nobody ever says, oh, we installed the new program yesterday and now it doesn't work anymore. Or the network team replaced all of our switches yesterday and now it doesn't work. Nobody ever says that. Nothing has ever changed in the world of computing. It just gets worse and worse. Okay, is it slow for everybody or just the person who works 1,000 kilometers away in the forest office has a terrible network connection? It's happened. And how slow is slow? So to me, anything that I can measure is too slow. I was at a customer site many years ago and show up on the first day and the IT manager has a stopwatch in his hand. And that's how he measured the screen response time. You click submit, click, 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 click. 10 seconds later, it refreshes and he stops it. That's how he was doing performance measurement of his system. So it's really important to be specific, just exactly what you're talking about. So from those questions, I start to identify what people are talking about. I quantify how much, how strong, how bad. We document it, we write it on a piece of paper, and then we put up some graphs, which you'll see later on, so that everybody gets a visual of the trend is better, the trend is worse, everything was fine, now it's terrible. Makes it very obvious. Oh, on Tuesday last week, we had the problem. It was fine before, it was bad afterwards. These are very important things to do. As an IT professional, if somebody comes to me who also claims to be an IT professional, and he says, oh, the file copy is very slow, or it takes 2 minutes to run this program, I don't want to hear it. What I want to know is, how much CPU time did it take? How many IOs did it take? And how long did it take? And those 3 pieces of information immediately give a hint about, is this a CPU problem? Possibly. Or is this an IO problem? Possibly. I have other examples of where the time was 2 minutes. It did no IO and no CPU. What else do I know? Oh, it's waiting for something. Is there a delay in the code? Sleep for 10 seconds? Is there, we're waiting for the user to push return? I don't know. But again, these 3 things together will help you understand terms like latency. How long does it take to do one transaction or one disk IO or one network operation? And then the rate. Can I do 10 megabytes a second? Can I do 2 gigabytes a second? What do these mean to me? So build the picture. Then possibly we can start talking about why. Maybe. So since the dawn of time, since the Manchester Atlas back in the 60s, computers basically do the same thing. Okay, nothing has been invented that matters to us. They're executing useful instructions. If you're calculating prime numbers, we're calculating prime numbers. If you're doing weather forecasting, we're building big meshes and models and applying transformations to them as they go along. Or they're waiting. You're waiting for a disk, you're waiting for a network, you're waiting for a human being to do something. You're waiting for more CPU time. Got a big computer with 8 CPUs in it. I've got 50 programs running at 100% CPU, and so I don't get any CPU time. It's not my fault, you know. Disk and network maybe is my fault. Human is easy. And then there's overhead, which is the operating system doing its thing. Mutexes and spin locks, or different things that have to happen in the operating system. Sometimes that number is very, very big. Mostly it's not. So you arrive at a customer site, and the HP sales guy is there in his nice suit and good looking. And he says, oh, I just sold them the best, fastest computer that I have in the catalog. It's also the most expensive, but that doesn't matter. And their application isn't any faster. Why? Well, modern hardware is really good, but trying to fix a performance problem with hardware as your first step, just blindly, is a great way for that salesperson to get a new boat, but it may not be addressing the problem you're having. A new computer might be 20% faster in the brochure, but on the ground, it might only be 5% faster or 2% faster than the old one, because you never had a CPU problem to begin with. And so resist.
But that's also one reason why they don't like us on site, or at least the salesperson don't like us on site, because we are too honest. Because I was in a customer who had a problem, and again, like Noam said, you asked a question, etc., and the sales guy told them already, I upgraded, faster CPU, bigger box, etc. But the problem is an IO problem, and you don't fix it with CPU. And then you go back and tell them, look, you just spend money on something which doesn't really solve your problem.
Yeah.
And that's why it's
Or another example, that you go visit the customer site and they have a brand new 3-node cluster with the best VAX in the world inside of a glass walled computer room, raised up right as you walk in the building. They're so proud. Work for a half a day and you're like, yeah, the best thing you can do is turn off 2 of the computers because you bought too much. Again, the sales guy, not too happy, but you have to be honest. Even when the answer is buy more computers, you still have to be honest. So many years ago, I was working, this is one of my coworkers at Oracle, and we were working on some difficult stuff, and it was frustrating. And this is a direct quote. And this is important, okay? Complaining about something is not going to improve it. No matter how passionately you want it to be better, you're gonna have to do some work. It's not gonna get better on its own. All right, let's talk about some experiences. So all of the examples that I'm going to and the stories I'm going to tell you are true. Sometimes you might be able to figure out who I'm talking about, but I hopefully not. I tried to protect everybody's identity, and that's because I used to say who it was, and then I got in a lot of trouble because we don't want people to know who I work for because it's embarrassing to them. Okay, where have the rights gone? So we helped a customer. They're deploying some new systems, and we did, they put the hardware in, we copied the software over and reconfigured the cluster and all this stuff. And they start testing it, and a couple weeks later, the database administrator comes back and says it's much, much slower. Now, I know that the computers are faster. I know that the storage is not slower. I mean, it's newer, better storage, but it's not slower than the old storage. Same network, same SAN cables and everything. And yet it's 3 to 4 times slower doing this database restore and recover. The IO counts are the same. So again, the first thing you look at is the IO count. CPU time is similar. There's a couple of anomalies here that aren't really all that important to what I'm talking about. And yet you can see it took much longer to restore and cover this database. So I know the IO counts are the same. The CPU time is kind of irrelevant in this case. So what do I think? I think, oh, there's a storage problem. There's a problem on the SAN. We're doing the same IO count and it takes much longer. Unfortunately, I was wrong. It's good to blame the SAN people. It's good to blame the network people because they never work in the same team. So host-based mini-merge is a feature of volume shadowing. And the idea is if I have a big system failure, if I have these bitmaps in memory, it can make the recovery faster when I have to put these shadow sets back together. However, host-based mini-merge is really good at that, and it's, in this case, you'll see, terrible for runtime performance. I care about runtime performance. What happens in your disaster doesn't matter to me. So what we found out after a short while was on the development system, we had no enhanced shadowing features at all. So you do a write IO, writes to 2 shadow members, and you're done. Their existing production system has these relatively large bitmaps, so I don't frequently overflow the bitmap and then have to flush it and do all this extra work. The new production system, for I don't know why, has relatively small bitmaps. And what they were comparing was their development system with their new production system. And so when we have these host-based mini-merge, bitmap, yada, yada enabled, I write to disk, but I also send other messages to other members of the cluster saying, this block of data has been modified. And there's optimizations. I won't notify you multiple times and all this stuff, but that was the difference. And so from the outset, oh, our new computers are slower. Your new computers are faster than the old computers, but the configurations were different. So again, a little bit of analysis, elapsed time, CPU time, IO counts, and we end up here. And then we fixed it. Now, I wasn't involved in the fix. What I would have done is I would have set the thresholds to 5 million so that it's better than the production system. So it looks like we've done a good job. Do you want to do this one? The IMB? Okay. All right. So SCIs, we rep the Karen emulator, and that emulates the alpha computer on top of a PC. So we deployed at some customer site in, I don't know, Maine or something, and everything runs great. Application works, system's reliable. However, this graph here is interrupt stack time. And the interrupt stack on VMS is sort of where the processor mode when IO happens. It's a little bit of a lie, but it's not important. So you can see on the left-hand side of this chart, it was hovering, 7, 5, 7, 10%, somewhere in there, some number. The migration is when it goes up to 30%. This makes no sense. I mean, there's really no justification for why this would happen. So we scramble around and look at charts and graphs trying to correlate. Are they doing more IO? Are they doing more telnet set? I don't know. And we narrowed it down to, this is related to doing lock traffic in a cluster where one computer has to talk to another computer and tell it something about a lock or to do something. So I eventually figured that out, and I built a tiny little set of programs that just do lock requests to each other within our cluster. And sure enough, I get the exact same behavior, which makes me feel good that I can reproduce the problem, but bad, I don't know why. So I started doing some CPU probes or some instruction counts at interrupt stack time. What instructions are executing? What parts of the code are frequent? And eventually I stumble into this one instruction inside of the middle of the cluster communication code, and it's called an instruction memory barrier. And that tells the processor that you've modified code in memory, executable code, and the processor should throw away all of its caches. This in turn, so I find the source code comment from a long time ago, from somebody we know very well, somebody I know very well, and it says, work around the hardware issue until a firmware update is available. This introduces an artificial stall to allow the EV6 hardware to do the right thing. Well, more and more analysis, there was a bug in a EV6 processor model where under some unknown conditions, it would take the wrong branch. Like I would say, whatever, if A is greater than B, then go to this instruction. Well, it would do the wrong thing. And the solution was to install these instruction memory barriers.
Punish everybody.
And punish everybody always for, as it turns out, 20 years. So I know that the emulator does not have this CPU bug in it. So I turned around and patched with patch/absolute, and I replaced the instruction memory barrier instruction with a no-op. And it occurs 6 places in this module. Deployed it on the customer site, and now they went from the, whatever it was, 35% CPU time back down to 4. So this was an interesting problem because it was kind of our fault. I mean, we installed the emulator. It was exposed a problem, an opportunity in VMS since 20 years. Again, follow the evidence, follow the evidence, follow the evidence. I could have told them, oh, you're doing too many lock operations, or could have taken the emulator back and put them on old hardware. So does anybody use FTP? Does anybody copy files over the network with FTP or DECnet or SCP? Yeah, everybody does. No computer exists in isolation these days. So we got a call 10 o'clock in the morning on some random Wednesday, whatever, in the middle of the week. And the customer says, we are seeing performance issues beginning yesterday. Okay, so go back to my first slide. What is it? Performance issues of what? So what they were really talking about was the throughput of an FTP copy. All right. They said the development machine is fast, production machine is slow. So our good-natured souls started checking and evaluating everything. We ran memory performance tests and disk I/O tests, bandwidth and latency, and checked their SAN switches and had their network team look on the performance monitor and all this stuff. And somewhere in the middle of this, we realized there's nothing wrong. Everything is fine. So the customer, it's the middle of the day, now it's probably 2 o'clock in the afternoon, decides, well, let's just reboot the cluster, all 6 nodes in the middle of the day to see if that makes this better. So we did. Of course, it doesn't have any impact. I mean, the problem stays because we never really knew what the problem was. Nice. It's probably them. And so dig a little deeper, dig a little deeper. I try to reproduce this problem on my system in my office. I can't do it. So unbeknownst to the naive reader, FTP and TCP/IP on OpenVMS includes a speed limit, a knob, which says go slow or go fast. And this FTP WNDSIZ. Okay, why are you trying to save characters in the name of a logical? Okay, include more vowels. Put another underscore in there. It'll be okay. It's not going to matter. But the documentation says changing the size of the buffers can improve network performance. Do you want me to make them bigger or smaller? How do I know if I'm having this? Anyways, so as it turns out, the development system had this logical name set to 1,000,000. The production system was set to an entire 4,000 since ever. I mean, since years and years and years. So we obviously changed the development system to be 4,000, so they were both slow, and now they can't compare them. So what are the lessons from this little story? Okay, first of all, don't believe anything that you're told. Customers always lie, okay? Show me, I don't believe you. Nothing started yesterday. It's been this way since decades. Having a group of people making decisions and analyzing problems can be very, very dangerous because human beings, by their nature, by the way our brains work, tend to follow a path, a leader. We tend to operate as one unit. And so once somebody says we should reboot the cluster, nobody's in a position to say, that's a really dumb idea. Okay, we have no evidence that there's a problem with this cluster. Specific problem statements, identify, we're doing 10 megabytes a second here, we're doing 100 megabytes, whatever it is. Be specific. Follow the statistics, follow the graphs. Don't reboot systems just because that's what you do on your Windows machine. It doesn't happen. My friend Christian is going to talk about this next section, which he has never seen before about right now.
Actually, this is pretty new, probably less than 2 weeks or whatever.
Less than 2 weeks.
Yeah. So Norm reported a problem that the I/O queue lengths, like how active, how many, if you do IOs to a disk, if you have many, they have to queue one behind the other, and there you can do a monitor disk item queue length, and you find out which are the busy disks. So again, is this graph was doing almost nothing. And then, okay, maybe a month ago it started before, but I only heard about it since about 2 weeks because he wasn't sure what he was seeing. So suddenly goes up to whatever, 4,000 and higher, 5,000 IOs. And actually he looked again. I mean, do you have the one from the? Yeah, there's almost no IOs going onto the disk, but it's busy. Like when he saw the monitor item, disk item queue lengths, and looking monitor mode, there's idle, nothing going on, nothing going on. No disk IO, but still the queue lengths high up. So does he have a busy disk now doing hidden IOs? So in the end, when he reported it, the first thing I asked him, are you doing any fancy IOs? Because I know he doesn't always do the standard way. So he said, oh, yeah, I'm using fast IO. And we have a lot of features, and we talked about that this morning. The normal copy is slow. Fast copy from SCI using fast IO is much, much faster. So I already know, okay, because otherwise, where do I start looking? So fast IO. And then the next thing he said, oh yeah, we have also bound volume sets, which is again from the 80s when you had those 400 megabyte disk and you need to bring something which has a couple gigabytes, you put them in bound volume set. So in the end, what it turns out, it could, because I tried to reproduce it on my system, I didn't have anything. So I made a couple LD container logical disks, bound volume set, did IOs and everything, but exactly same program. I couldn't reproduce it because first of all, LD doesn't do fast IO, but it doesn't tell you. You can issue fast IO and they will just turn into slow IOs. But in the end, to come up with the real fix, I mean, so we had like a 5-member bound volume set. And the key to the fast IO is you do the setup and everything, and then you reuse the same IRP, the IO request packet, for all the IOs. So the first IO has to go to the second volume, the next IO has to go to volume number 5, and the other one to volume number 0. And of course, every time you reuse, you update the UCB field where it has to go to which disk. And you increment the queue length, and then afterwards you decrement. But it was always decrementing the one from the first volume. And incrementing, no, it was incrementing the one from the first volume, but it was decrementing when the IO complete the real IO to the real, and it went negative, but it said queue length cannot be negative, so we just set it to 0. Otherwise, you would have seen a lot of disk with a negative queue length. So basically, the fix in the end was there, like when we update the UCB for the particular IO, we need to do that before we increment the queue length.
But you didn't play your own game. There was no problem. It was only a visual.
Right. Yeah, I'm trying to fix the graph.
Yeah. I mean, it's like, of course, like you said, there's no problem, but somebody reports that, and then you say, okay, what has changed, and is there a real problem?
What is your real problem? No.
And the same thing what you said before, this customer, I don't trust customers. I said, I go with data. Give me data. So they give me data, they give me the product. It's like, so the fix is in there, but it hasn't been released yet.
But yeah, it was, I mean, as Hein mentioned.
The case hasn't been updated at all.
And of course, any regression test we do today, they will not catch that because very hardly anybody uses this combo of bound volume set. Because the disks today are much bigger, and so.
But yeah, I was trying to tune the graph.
Yeah.
At the end of the day, that's where the time went.
Okay.
All right, so this is another discussion similar to what we saw before for a completely different reason. So I don't know if you can see this graph real well, but again, this graph is interrupt stack time or interrupt state. And so you can see during the day, there's a little spike because all the users are busy doing user things, and at night, nobody's there. Everything looks fine until whatever it is, August or something. And all of a sudden, interrupt state peaks out at, went from 20% during the busy times it's 100%. Crisis, oh my gosh, we need to fix the graph. And that's something internally we need to resist the temptation to, like, just because the graph moved, there might or might not be a problem, but it's, customers usually call us when it's a crisis. We don't need to go look for them, they'll find us. So we start to analyze this and look into it. And of course, oh, no application changes, nothing changed. System, nothing changed. The application, nothing changed, except for the graph. So what I found out was the TCP packets didn't change. There's a little more network activity, but not much. All the DECnet counters stayed. There's no evidence of what's happening. So I started running Wireshark. Somebody, do you know what Wireshark is? Okay, conceptually anyhow. So I started running Wireshark and looking at the messages coming in. And it dawned on me after a while, boy, there's a lot of telnet activity on the system. Awful lot of telnet activity coming in and going out for not very many users, for not much apparent work. On and on and on. So what eventually they admitted to was, oh yeah, our IT department is rolling out new desktop environment. You get a package on your desktop, new software and all this stuff. They upgraded their terminal emulator, which I can't remember which one it was, one of the free terminal emulators, to the latest version and gave everybody a fresh configuration file, which included this thing that I never knew about, but there's a telnet timing mark part of the protocol that does nothing. It's just a little placeholder. And inside of TCP IP on VMS, when you get one of these little placeholders, you throw it away very early on because it's sort of a no-op in the protocol. So it gets thrown away before it even gets processed by the rest. And so we don't see it. They set this to 0 seconds. Now, most human beings would say, oh, 0 seconds means disabled. In this terminal emulator, 0 seconds means don't wait. So their terminal emulator on their desktop is sending these messages as fast as they can, along with the other 30 people in the office who are connected to the system. And that's why you see interrupt state time go to 100% and just stay there, because it can't do any more. So after much negotiation and the desktop IT people claiming it wasn't them and this and that, and I convinced them to say, just tell you what, try set it to 300. If it doesn't work, if you don't like it, we can put it back to 0. And so, of course, they set it to 300. That's why I'm telling you the story. And everything is fine. But the VMS system has this terrible problem that's none of our fault. Nothing changed. Everything was wonderful. They made a poor choice. This next section is special for Hein. So, all right, so we do database administration for customers as well as VMS administration on RDB. And since years and years and years, when I was an engineer back at Oracle, we would tell people, oh, you must use this ranked index feature. It's our flagship, newest technology. It's got all this wonderful pseudo ranking capabilities and compressed bitmaps with a patented algorithm and all this stuff. So I've been saying this for decades. And so this application, just like Hein's examples, has a column in the database. It's basically processed. Okay, a new record comes in, it processed as 0. We finally get around to working with it, do whatever it is responsible for, and set it to 1. We only ever care about the records that are not yet processed. Once they're processed, we'll never see them again. So now SCI does a RMU analyze index, and it says, oh, this index has 1 million duplicates in it. And being the superstars that we are, we come in and say, we can solve this problem. We'll turn this into a ranked index, and now you'll have no duplicates. Unfortunately, the next day, the customer calls up and says, we're having terrible performance problems. We're having lots and lots of lock conflicts in the index. We have detected deadlocks that are to be resolved internally. It's awful. I mean, performance went to heck. Now, of course, this isn't our fault. So we start looking around for other things that might have changed, and it was us. Now, why? So historically, RDB, when you have a duplicate entry coming in, it puts it, the new entry, it puts it at the front of the chain. Okay, so we go to the first place on the chain, we stick the duplicate. When I go looking for things that need to be processed, I take it out of the 2 or 3 or 10 elements that have to be processed, and I put it on the end of the already processed, or the beginning of the already processed chain. Works fine, lasts a long time. 3 IOs. So it's reverse chronological order. Things go at the beginning. Now, what's the downside with this model? Well, if I say delete all of my elements that are more than a year old, I have to traverse the chain all the way to the end to find the record that I'm going to remove from the index. So it takes forever. But nonetheless, it works great for this customer's application. RMS, in contrast, as we learned yesterday, does it the opposite way. RMS's rules are everything is in chronological order, and so the duplicates go at the end instead of the beginning. Good, bad, or indifferent, if you delete the oldest record here, it's very fast. So over time in RMS, it gets slower and slower and slower to insert a duplicate because we keep following this chain, which gets longer and longer and longer. Such is life. The RDB sorted ranked index takes the worst of both models, and we store it in this logically infinitely sized bitmap that's compressed down to little pieces with good technology. We store it in the bitmap in physical address order. So not soonest, not latest, but somewhere in the middle. And we have to search through the whole chain, and then we have to put this bit back in the correct place. Again, in real life, what it means is as I put more and more and more records in my database grows. So my physical addresses continue to grow. So I keep putting them at the end of this chain. Again, we thought we were doing a very good thing using all this good technology, and absolutely ruined the customer's application performance. So a good learning for us is the correct solution is not always the correct solution. Apply your changes with some amount of safety, of doing the right thing. Does all this make sense? I know it's kind of technical, ugly, and I've got these little PowerPoint Excel graph things here, but how are we doing on time? So I was asked to go to a customer site and deal with a performance problem. And the backstory is this was at the very beginning of COVID, when the stock market was extremely unstable because nobody knew what was going to happen, and are people going to die, or business is going to be shut, is it going to go away? So trading volumes went up, and unfortunately this customer is in that business. And within the previous year, their board of directors or somebody said, you know, your primary data center and your DR data center are awfully close together. In fact, you can just about walk from one to the other in a reasonable amount of time. They say, oh, much too close. If a bomb drops, you know, we need to be able to keep the stock market going. Now, I don't know about you, but I feel like a bomb big enough to take out both of your data centers, the least of your problems as a society is the stock market. The millions of people that are died, but this is more important than life and death. This is money. So because of that, they moved the other data center to, I don't know, 30 kilometers away, something, I don't remember. And they bought the best possible network technology, ultra dark fiber 3000 with the turbo option and parallel redundant links from 2 different vendors. And they must have spent millions of dollars a day having all this super infrastructure. Unfortunately, as we'll see, the end of day processing gets much slower. But they were getting by. Nobody cared until COVID hits, trading volumes go through the roof. Now they cannot get their end of day processing done overnight. So their overnight batch goes into the next day. Bad things happen, apparently. According to them, that's bad. So why is this? Well, a portion of their application, this is moving money around. And it's very important that when I take money from your account and give it to somebody else, that's an atomic transaction. That's one event moving this money. And to do that in modern computers, we do one disk IO, a little one, to say this event happened. So if the IO is on disk, it happened. If it hasn't made it to disk, it didn't happen. And that's the database, point of consistency, transaction commit, whatever you want to call it. They implemented this on their own. So they do single block IOs to a great big file. During the day works great. You can do, 1,000 IOs a second or whatever it is. At night, though, they reset all of these logs. And the process of resetting uses the same machinery. So they read a block of data, look at it, and then write it back as all zeros. So they erase it. And that took a long time. So they moved their data centers. Now they're getting into problems every day. So I said, rather than move your data center back, which was one of my suggestions, is like, can't you just go back to the old data? Oh, no. We built a new building. Got to use it. So instead, I said, why don't you copy the file off of disk into a DEC a memory disk inside the computer, and then do your little reset job, and then copy it back. 3 lines of DCL code, everything else won't know the difference. And I tried to graph this, and I apologize in this room, it's a terrible looking graph, because all I care about is over here. But before they moved data centers, they were doing 1,200 IOs a second overnight, and that's about the limit of what you can do to write to 2 data centers. After the move, it was cut in half. So what do we know? Well, the data center moved twice as far away, so that's why it takes twice as long, speed of light being what it is. And the time it took twice as long. So if it used to take, 1 hour, now it takes 2 hours, speed of light being what it is. So I show up with all these fancy ideas. Now they're doing 30,000 IOs a second. So this end of day job gets done in about 8 seconds. And I said, I can make it faster. We can do some other tricks to squeeze that down more. And like Hein said, all right, I already made it 120 times faster. There's no point in trying to squeeze another 2%. I was extremely unpopular because the overnight operator crew would start this job and then go out for coffee and come back and watch it complete. So I got in trouble the next day. They're like, oh, this is awful. You've ruined our evening. So what did we get? Their overnight jobs became 30 times faster. They gained an hour of the 6 hours that they have to do all this work. So they went from not being able to accomplish overnight to being done in no time. 3 lines, effectively, 3 lines of DCL code. But again, follow the evidence. Where is it slow? Why is it slow? What can we do to make it better? And resist the temptation to make it perfect. Okay, better is usually enough. Not always, but mostly. Okay, so also during this, so now I have some credibility there, and they start to ask me questions. Oh, this other process takes a long time. Another danger of looking too good is that they want more. If you just look okay, nobody asks you for more. If you make it really fast, they think you can do it again. So Another part of the overnight process is we have to take all the trades from 2 days ago and delete them from the database because they've already been settled and cleared. They're done, and we don't need to carry them around any longer. So they do what every programmer in the world would do and say, delete from the database where process date is 2 days ago and settled status, and took an hour and a half. So I said, instead, why don't we read the list of DB keys of the records that we're going to touch, and that just traverses the index. So I don't have to read all the data records. I have an index which gets the job done. Sort that list by physical address in the database, because it's in a file now. Drop the indexes off the table. Delete the records by DB key, which means every page in the database will only be touched one time. Usually there's 50 records on a page, so I'll delete them all at the same time. And at the end of the job, delete or recreate the indexes. So I make one pass through all the storage areas, another pass to recreate the indexes, and it's 3 times faster again. So follow the evidence. What's slow? Justify every IO. If inserting a record in the database takes 40 IOs, why? What are they? Where did they go? What were they doing? All right, we're running a little slow on time. I'm trying to think if there's any. Okay, I'll tell this one. All right, so different customer upgraded one of their systems to RDB 7.4. The customer comes back and says, oh, some random job is now 5 times longer in our new system with RDB 7.4 than it is in production. Something's broken with RDB 7.4. I know this is not true. I know 7.4 is at least as fast as 7.3, a little faster in some cases, but not slower. Same amount of CPU, same number of IOs. Well, in fact, RDB 7.4 was slightly faster than 7.3, which changed the relationship between all of their batch jobs running, where maybe they used to run kind of in this sequence, and now they run kind of in this sequence. And there's another process in the database, and I'll bore you the technical details, basically, that's blocking everybody else for, 1 minute and 2 seconds. So the order of events meant that somebody got done a little faster and now blocks everybody else for 2 minutes. When the first process commits its transaction, everybody else finishes on time. And so I just said, well, why don't you reorder the scheduling of all these things? Everything will be great. But what did we change? We upgraded RDB 7.4. Their application got a bunch slower in one of these processing steps, not because anything was slower, but the order of operations. Doesn't matter. Okay, what do I want you to walk away from? I mean, the stories are fun and there's interesting learning and so on. Okay, got to take action. You cannot have, as Christian described, you can't have a broken arm and go to the doctor and say, you can't touch me. Like you can't fix it, but don't touch me. Okay, you have to make changes. If you don't make changes, nothing's going to be better.
The problem doesn't go away.
Yeah, none of these problems will heal themselves. And like I said before, perfect is the enemy of done. I want to get in, make the 80 or 90% solution and leave. To get to 100% will take the rest of my life. So make it better, make it good enough, make it exceptional, but move on. Don't make it perfect. Because, and this is the first quotes from a race car driver, he said, 100% will not make the grid of the race. In other words, if I wait till my race car is perfect, I'll never be able to start another race. I cannot win if I don't start. If I can't put something into production that's better, I've not done any good for the world. Don't be a perfectionist, okay? Be an empiricist. I got what I was after. You know, I made it faster. I invested a couple of hours. Everybody's happy. If I make it twice as fast again, nobody will care. Nobody will know. You know, the difference between 1 minute and 30 seconds instead of 2 hours.
But I might get in trouble for saying that. I see the same thing at VSI. I mean, we develop and we test and we test and we test again and we test for half a year before we have the courage to ship something. And then he runs it for 1 day and he finds a problem. It has been like that for years, 20 years ago. I mean, sometimes it's the customer, they have totally different configuration, totally different thing. And that's also at one point you have to say, okay, we test as good as we think we can test, and then ship it and expect problems to happen instead of waiting another half a year and the problem still happen regardless. I mean, you have to kind of find the right balance. I mean,
so there's a good story that fits this. After the Space Shuttle Challenger disaster, a blue ribbon panel of scientists and engineers and senators and all these things analyzed what happened, and they found all sorts of different things, which isn't important. But one of the things that they found was that the software testing and the software engineering was exceptionally good. They said the software development was very good, to the point where they wanted to reduce the software testing because they never found any bugs. So they wanted to save money by testing the software, or by reducing software testing, because it must not be very good because it never found anything. The job of software testers is to break things, not prove that they work. That's a good testing environment, is they can break it. I don't want to know if it works. I know it works. I wrote it. I want you to find where it doesn't. Collect your T4, collect statistics, store it, graph it. This is, I don't know, buffered IO rate mapped over a couple of months. I would never in a million years notice that for 4 days, we had this huge, long running problem, and then we killed it and it went away again. But if you're not looking at data at this level of overview, you'd never notice that, because you come in on Monday, everything looks fine, but all weekend it was broken. So collect your data, review your data, look at it. Other hints that I tell every customer, and nobody does it, so please don't do this because nobody else does. In your command procedures, do set verify and set prefix. So you get timestamps in all your log files, your batch log files. So when you call me, I can come in and say, well, this step was done at 2 o'clock and this step was done at 2:10. 10 minutes of your whole job was in these 3 lines, these 2 programs. Otherwise, you ask the customer, what happens in this command procedure? Oh, we don't know. So don't do this, please, because nobody else does. And I don't want you to be better than they are. Hein will tell you that these first 3 steps I've listed here will do you all a lot of good. At the end of the day, do something rather than nothing. Does anybody here compile their application /no optimize? So no optimize is actually a French word. It's no optimiser. And it means in French, go slowly. Okay, you're explicitly asking the compiler to produce slow code. Ask yourself if that's really what you want to be doing.
it's just that the debugger doesn't jump up and down.
Yeah, it's easier to debug. So I have another an example of this. Big trading system that you've heard of that people spend millions of dollars to buy and deploy. It runs all over the world. They compile their application /no optimize.
Because in 1978.
Maybe there was a difference. Or what they told me was, well, if we ever have a problem in production, then we can debug it. Okay, how many times in the last 2 years have you had to do this? And they talk, oh, never. If you guys sort any data, try hypersort if you haven't, and nobody has. It's buried on page 842 of the utilities manual. And so when you've read that far, you'll learn about it, but it's much, much, much faster. All right, we're done. Evaluate. CPU time and elapsed time is your biggest clue of where to go next. The big hints, CPU bound, it's IO bound, something that doesn't make sense. It's doing no CPU and also no IO. It's waiting for something. I don't know what. Interview, isolate, identify. Thank you for coming. I apologize for running long.